Okay, so I'm going to go through the second half of this module. The last two objectives will be under direct current motor principles now. So we talked about generators, so just got to kind of put it in our head that we're talking about motors now. Okay, and again, a big difference is between the generator and the motors is how they're used. So a generator, we have a motion usually from mechanical means, a combustion engine, something that's turning that uh, rotor within the magnetic field that converts basically mechanical motion into energy. Now we're going to hook electrical energy and create mechanical torque that produces motion. So just kind of keep that straight. Now we're talking about motors. We're applying a voltage to the commutator segments, and then that's going to create the developed torque or the Lorentz force that's going to start turning the motor. Okay, we did talk about this in third year a bit too with squirrel cage induction motors. So they talk about motor action in generator. They don't really talk about it much in the generator portion, but there is a motor action in a generator where we have the two fields interacting, and it does create a developed torque that opposes the torque applied by the prime mover. Now, that's literally all they talk about in the module, so you don't really talk about it too much. But it does happen in a generator too. So the torque in a motor, the same action that develops it in a generator also does it in a motor. Just the torque in the rotor opposes the counter torque applied by the load on the motor shaft. So again, these motors are hooked up, spinning, and hooked up to drive a load. Okay, so when we put that load on, that's the counter torque applied by the load. So the force that causes the armature to rotate is produced by the interaction of the two magnetic fields, one from the armature winding and one from the field. Again, we have the field winding that is an electromagnet, and then we have the armature windings that have voltage being put to them because this is a motor. And then depending on when we have a load attached, going to draw current through those armature windings. So again, the Lorentz force is a force that tends to push a current carrying conductor at right angles to a magnetic field. The direction of the force can be determined by the right-hand rule for motors. So we have this right-hand rule that's basically going to show us which way the conductor is going to want to move when it's in that magnetic field that has current going through it. So we use our right hand. Again, we push our index finger in the direction north to south. This is, again, our only right-hand rule. Our middle finger is going to show us the direction of current, and then the direction of force will be shown by our thumb. So that is the force that the torque is going to try and push that conductor out of the way. So we kind of can see it a little bit better on this picture, where we have current going through these armature windings. Okay, so that's the current just like we see going through this conductor here. The current going through the conductor here on this side creates a magnetic field around it, and that's distorting the main field. And again, if we remember what happened with magnetic lines of force, they want to straighten themselves out. Okay, there's a force there that's going to try and straighten them back to their shortest path. So when we have this bending of the field, plus if we use the even the left-hand rule for conductors, we can see that the magnetic field around this portion of it, so we'll just look at this portion of the armature here, we have an excess of magnetic lines of force basically lining up going the same direction as the field. So the field's going from north to south. Here it's canceling out, but here it's aiding, if you will. So we have a stronger magnetic or an increased density here of lines that's going to want to try and push this down this way. And at the same time, it's happening over here just the opposite way because the current's going the opposite direction, which is going to push the force, is going to try and push it up. So we have one side pushing down, the other side pushing up, and we're going to get this thing to spin because it's sitting on bearings and is able to spin freely. Okay, so this is probably one of the better pictures, I would say, to help show us that. If we use the right-hand rule on this side here, again, we go from north to south with our index finger. We show current coming out of the page, so that's our middle finger now pointing towards us, and then our force is pushing down. So our right-hand rule will show us this force as well here too. Okay, but again, it's all about that torque being developed because we have the interaction of two magnetic fields. So when we talk about generators, we talk about generating a voltage, okay, a usable voltage so that we can hook up anything to this DC generator and have an applied voltage for us. Now there is a generator action in a motor as well. So there's a development of a voltage. Even though this is have a voltage applied to it, there's another voltage that's developed, again, because we have a conductor moving within a magnetic field. So it says the current creates a magnetic field, and when they interact, they produce torque on the motor, resulting in rotation. Okay, so we just talked about that. The rotation of the rotor causes the armature winding to cut across lines of flux from the field winding. So now this starts to rotate based on the Lorentz force on the conductors, start to spin it around within the field. Well, as it spins around, it definitely has a voltage induced into it. So this says this causes an induced voltage in an armature coil that is opposite in polarity to the applied voltage. The induced voltage is called counter electromotive force, or CEMF. So when it's rotating, it generates a CEMF. So again, that's not the job of it. It's not producing a voltage for us to use, but it's happening because we have a conductor moving within a magnetic field. Okay, so it talks about how we can find out the direction of that. We can use the right-hand rule to show the Lorentz force, so we can get that the conductor is going to be moving up this way based on the north and south and the current flow through there. Okay, and this current here. And then it's saying to use a left-hand rule, where we're going to put our thumb in the motion conductor. We're going to use our index finger, again, through the north and the south. And then our middle finger is going to point in the direction of the generated voltage. Now again, it's generated voltage, it's opposite that of the voltage that applied. Okay, so basically the long and short of this is saying that this is how we can see that the EMF that's developed is in fact counter to the applied. Okay, so there is a CEMF in a motor that's generated just like in a generator. Okay, the only difference is it will never be the same as the applied voltage, never be the same value. Okay, so the magnitude of the CEMF is dependent on the same factors as the output voltage of a generator, and to calculate it, we can use the same equation. It's just that now E-gen is now CEMF. Okay, otherwise it's the same formula. So the value of the CEMF when the motor is running is lower than the value of the applied voltage, so it will never reach that value. Okay, the effects on the motor of generated CEMF. So the instant a DC motor is started, the armature is not yet turning. Okay, so no CEMF is being generated because we don't have that motion between the armature conductor and the field. So at this time, the only thing limiting armature current is the small value of DC resistance in the armature, which is usually less than 1 ohm. Again, very small. So with our applied voltage and only the very small resistance of the actual armature, we get extremely high currents on start. Okay, so 120 amps. As opposed to when we start to spin and we have CEMF generated, now we have a value of CEMF that's basically going to counter the applied voltage, and the resultant is what we're going to use to determine the current flowing through the armature. So as it starts to turn, it builds CEMF, which limits the current in the armature. It went from 120 to 10 amps. Okay, and that's because this is counter, so it's going to cancel out some of the applied voltage. This is an important thing is under startup, we're going to see extremely high values of current. Okay, so we would have to potentially count for that so that we don't have destructive effects. We'll talk about that later when we talk about the different types of motors. So then we have a fundamentally motor equation, again derives from Kirchhoff's law that the total applied voltage has to be equal to the sum of the individual volt drops. So here's our fundamental motor equation. So this is the applied VA. We're going to have our counter EMF, and then the portion that we have to, the voltage that we need basically to provide current for the counter torque for the load is, and plus the CEMF has to equal the applied. So they're going to have to give. If this goes up, this goes down, okay? Because they do actually have to equal each other out still. So since torque is proportional to armature current, which means if armature current goes up, torque goes up. At the start, CEMF is 0. So the motor has high starting current and high starting torque, okay, directly proportional. As the motor speeds up, the CEMF increases and limits the current, okay, just like we saw in that previous calculation. The CEMF continues to increase until the difference between it and the applied voltage is a voltage that produces enough armature current to meet the torque requirements of the load. If the load remains constant, CEMF and armature current will stabilize. This is known as maintaining electrical balance. Since the CEMF is dependent on rotational frequency, okay, so we're going to basically induce a voltage based on how fast we're spinning in that magnetic field and the intensity of that magnetic field. A change in either one would result in a change in the CEMF generated. So when the load increases, the motor slows, decreasing the rotational frequency. So think about that. When I put load on a motor, it slows it down. So now the armature is not spinning as fast, so it's not cutting as many lines of force. So then it's not generating as much CEMF. If it does that, we increase the armature current, which increases the torque to drive the increased load. So then the motor stabilizes at the lower speed with an increase of torque and armature current. So and we've seen that if you've ever run a tool, a skill saw, a table saw, a drill, it spins as we're holding it in the air, spins freely. Once we put it under load, it slows the rotation down, which draws more current or increases the current and increases the torque enough to continue to do the job. Okay, how can we reduce the high starting current? High starting current can be reduced by, again, placing a resistance in series with the armature at start, then removing it, or applying less than rated voltage. So if we can drop that applied voltage and slowly increase that, we can reduce the starting current, that high inrush. This is what we'll do in the lab, this second one. We'll be reducing our applied voltage to limit the starting current so we don't pop fuses. So we'll see that. Armature reaction, again, very similar to what we talked about with generators. The biggest difference is that it causes the neutral plane to shift in the opposite direction of the armature rotation. So in generators, the neutral plane shifted in the same direction as the rotation of the armature winding, okay, or on the rotor, and in a motor it goes the opposite direction. Still have the same effects. Again, at no load, we have our neutral plane. Again, think that we're still sending source voltage through these, or applied voltage through these brushes and windings. So we want to do it at a point where they're not going to be generating a ton of CEMF, because we will get arcing and such at that position again. So when we have load, we have large currents going through here, again distorting the main field, shifting the, again, if we're rotating this way, it's shifting in the opposite direction, but still shifting, and potentially now the neutral plane is not aligning properly where we want to make our brush contact, so we can reduce that arcing and sparking. Okay, so again, we do get that issue. To avoid it, again, we can move the brushes, or we add the interpoles with commutating windings and compensating windings. Okay, so same kind of deal that we had with the generators as well too. Okay, now direct current motor speed. So speed is something we're going to talk about here specifically. And the speed, they talk about three scenarios that's going to affect our motor speed: the effect of load, the effect of magnetic field intensity, and then the effect of the applied voltage. Okay, so changing the armature voltage, and see how that affects it. So the first thing to talk about is the effect of load. So if the load or counter torque on the motor changes, the developed torque changes. So the developed torque is the torque that's being developed within the motor. Okay, so motor torque as opposed to load torque or counter torque. As load is added to a DC motor, the following processes occur. So it slows down, so we're asking it to do more. Okay, so we're putting more load torque onto it. As it slows down, the CEMF is less because we've reduced the rotational frequency, so we're not cutting as many lines anymore. The armature current now increases because CEMF decreases, and CEMF limits armature current. Then the torque increases because armature increases, and they're directly proportional. So the torque increases to equal the counter torque of the load. So basically the developed torque is trying to match the load torque so that it can still do its job. Okay, again at a reduced speed. Now, the effective magnetic field intensity. So again, this is our field winding. This is where we can have a rheostat in series with that and change the amount of flux intensity that that field has. Again, higher flux intensity, more generated voltage, or in this case, generated CEMF. So that has an effect on that. So if it's operating with the load and the field, so the load isn't changing now, we have a constant load, and the field intensity decreases, the motor speeds up. Okay, so why does that happen? So the armature coil cuts fewer lines of flux because we've decreased the field intensity. So now the CEMF decreases because we're not cutting as many lines in the same rotation. Now the decreased CEMF allows for an increase in armature current, again because this counter EMF is what limits armature current, and then the corresponding torque increases because they are directly proportional. The developed torque is now greater than the counter torque of the load, so it speeds up. So think it's almost like we have a scenario where now we're creating more torque than the load needs, so the motor's going to go faster. Okay, so with the increased speed, the CMF increases and then the current decreases until the developed torque and the counter torque are equal. Okay, so we will see an increase in speed, and then it goes to adjust and maintain electrical balance again. The effective armature voltage, third thing that we can affect is, when they say consider Ohm's law. So I armature is going to be the V applied over the resistance of the armature. Okay, so these are on the same line, armature current and the applied voltage, so they are directly proportional. So the armature current is proportional to the applied voltage and inversely proportional to armature resistance. Since the resistance is constant, a reduction in the reduction in the applied voltage results in a reduction of current. So if the applied voltage to a DC motor is decreased, the following changes in the motor occur. So we're decreasing the voltage. What happens? The armature current begins to decrease because they're proportional relationship. If the armature current decreases, developed torque decreases because they're directly proportional. Speed begins to decrease because of the reduced developed torque. And then the CMF decreases because of the reduction of speed in the armature. So armature current stabilizes when the electrical balance is achieved at the lower speed. Okay, so those are the way we can affect the speed. Those are the three ways we're going to talk about affecting the speed of a DC motor. This is just an example I'll go through with you guys here. We just want to be able to determine, again, we got to use the left-hand rule for polarity to decide which is the north and which is the south. And then we use the right-hand rule for Lorentz force, and we'll be able to see which way this is spinning. This is right out of your objective exercise. So I usually go through with this with the class just because it's one of the questions in the exercise. But I'll do it on the board when we do our lab. The effect of loading on DC current motors. Again, we're going to see how these can be hooked up to get the best possible effects for the different types of loads we have. So direct current dynamos, whether they are generators or motors, are all constructed with the same basic components. There are some differences in the design that optimize performance as either a motor or generator, but the basic field and armature winding connections are the same. Both DC motors and generators are categorized by the way the field and armature windings are connected. Okay, so they talk about generators and motors. We're mainly going to talk about motors. So shunt is basically the windings are connected in parallel. Series, they're in series, and compound would be a combination of series and parallel. So start off with shunt motors or parallel connection. So we can see the parallel connection here and here with the field winding and the armature winding. Now we have the same applied voltage across both of these because they're in parallel. The current splits along these two branches with the highest amount of current going to the armature winding because it's made of it's a large conductor with few turns. The shunt field winding is made up of many turns of wire. Okay, so a higher resistance, so we're going to see less current in the field winding. So again, they're saying 5% of the current going to the field on roughly and 95% going to the armature. So shunt motor and rotational frequency. The torque of a shunt motor is proportional to armature current, okay, which is directly dependent on the load. As load is added to the shunt motor, again, speed decreases. The armature is cutting less lines of force, so the CEMF decreases. The armature current decreases because the lower CEMF, again, limiting factor of the armature current. The developed torque increases as the armature current increases, okay, because again, they are directly proportional. So what do we have is actually the shunt motor is being considered a constant speed motor. So under various loads, we see a very small decrease in speed as we increase load, okay, with a substantial increase in torque. So again, constant speed, if that's what you needed for your application, you'd use a shunt motor. So our speed is changing, but a very small amount. Okay, and we get as we get a large increase in torque. Okay, so it can drive a load without really affecting the speed. Starting the shunt motor, again, when it's not running, the only thing limiting is the small internal resistance of the armature winding, which is low. So to restrict that armature current until the CEMF is generated, we would have to have a resistor in series with the armature winding. Shunt winding has a high internal resistance and needs no additional resistance. Okay, so just the armature winding, we would have to do that. Shunt motor runaway. Speed control of a shunt motor is accomplished by varying the shunt field resistance. If the field resistance is very high at start, so resulting in very low field current, so a weak or non-existent field, again, the current going through that field winding is what's creating our electromagnet. So if there's high resistance, we have little current going through, so very little electromagnetic flux going through that field. There would be little or no generated CEMF because as we're rotating, we're not cutting any lines because the lines, there's not that many there. So with no CEMF, the armature current increases to an extremely high value, resulting in an extreme increase in speed or runaway. Okay, so if runaway occurs, it can damage the motor. So adding a resistor in series with the armature winding during start prevents this hazardous condition. Okay, so yeah, we definitely want to avoid that. If we lose that field, we basically turn potentially into a series connection and have a dangerous situation. The series motor, field winding is connected in series. Okay, so obviously we have everything connected in series with the armature here and the field now. So both windings see the exact same value of current. Okay, so the currents that flow through the two windings can result in strong magnetic fields despite relatively few turns of the coil. So what does that mean? In a series motor, when it started, there's very little opposition to current. With high current and strong magnetic fields, a series motor can produce high starting torque. Okay, so that's an advantage for certain loads. If we have a very heavy load to start, or we need right from the get-go, we need to basically drive a huge, torque load. This is going to be your choice. Is we want to start this, and we want to start this motor under load. Okay, so once load is added, the CEMF generated restricts the current flow. If the load is increased, the speed drops, and the value of CEMF also decreases. Decreased CEMF results in higher current in both windings, and torque also increases. So again, very high starting torque. In a series motor, the torque is proportional to the square of the current, since the same current flows through both windings. Okay, so that's where we're getting that increased torque. Decreasing the load. If the load decreases, the motor tends to speed up. This causes CEMF to increase. Current and torque then stabilize at the new load condition. As load decreases, the current decreases in the armature and series field. So the applied voltage remains the same, so to maintain electric balance as the armature current drops, the motor speeds up, which then increases the CEMF. The series motor does not have a definite no load speed. So that means basically there's no speed where it says, oh, at no load it runs at this RPM. Okay, if the entire load is removed, the speed of the rotor may be above the safe operating speed. So the series motor must not be used for light loads and must be directly connected to the load. So we cannot start a series motor under no load, or it will just continue to gain speed, again until destructive effects. So like the series motor, the series motor, like others, follows the fundamental motor equation. The applied remains constant, as does the resistance of the armature. the current in the armature decreases as the load is reduced, and the CEMF or the speed increases to maintain the balance. Again, very huge caution here. Okay, they have to be started under load. They cannot be operated at no load. As load is added, speed goes down, CEMF reduces, the current increases to a value that develops enough torque to drive the increased load. Series motor can develop as much as 500% starting torque as compared to full load torque. Okay, so again, speed, definitely not a constant speed by any means, but extremely high starting torque. Again, has its purposes for specific loads. Compound motors, basically a combination of both, series and parallel, taking advantage of both. Has a series field winding in series with the armature and a shunt winding in parallel. Again, the series winding is made of few turns of heavy wire, and the shunt is made of many turns of a fine wire. So 2 ways we can hook up this compound, either cumulative or differentially compounded, one where the magnetic fields aid each other and one where they oppose each other. So cumulative compounded, again, aiding each other, so that designed so the current through both the series and shunt winding are in the same direction, so the magnetic field aid each other. Shunt winding can be connected in 2 ways, long shunt or short shunt. The long shunt, again, the shunt is field winding is paralleled with the whole series and armature windings, and the short shunt is when it's just in parallel with the armature. When load is connected to a cumulative compound motor, speed decreases, then again the CEMF decreases, armature current increases, and the series field intensity also increases. Okay, the shunt field remains constant. The series field, again, it would increase because it's in series with the armature. The shunt field flux and the increased series field flux combine to provide greater flux than a shunt motor alone would have. So this results in greater torque. So again, even though we have the shunt winding in parallel, with that addition of that series field winding with our armature, we do get an increase in torque that's a little bit better than the actual just the shunt. Not as good as the series, but better. So kind of a combination again of both. The way this motor reacts to load is similar to a series, but the starting torque is lower. Okay. Differential compound motor is used where a nearly constant speed is required. Again, not quite as constant as parallel, but this motor differs from the cumulative compound motor in only one respect, and that's that the current in the series winding flows in the opposite direction, so it has a canceling effect. Okay, so the series field opposes the shunt, which weakens the total field that the motor, so that the motor can speed up. As load increases, the subtracting effect on the series field lowers the CEMF and allows large series winding and armature winding currents. If too great of a load is placed on the motor, the series field intensity becomes greater than the shunt, and it can actually reverse directions. Okay, so a cautious some caution there with the differentially compounded motor as well. So here's the series winding in a differential compound motor wound in the opposite direction compared to a cumulative compounded motor, which again was aiding. So here's some comparison curves for torque for the different types of motors. So torque is proportional to the load. The shunt motor curve shows very little change in speed as the load is increased. So again, constant, that's the shunt. It's constant compared, again, differently a change, but not near as much. The series motor shows a large drop in speed as load is increased, and the cumulative compounded exhibits combinations of both. Okay, so again, series shunt got that cumulative sitting right in the middle, kind of doing the best of both worlds. The torque curve for the shunt motor is a straight line because the field flux remains constant. So again, this series, good starting torque. Okay, again, the shunt, not so good. It's more of a straight line, and then the cumulative compounded is in between the two once we go from our starting here to full load. So this is just getting up to those points. So again, the torque produced varies only with the changing armature current flux. The series motor curve does curve because the torque produced varies not only with the armature current flux, but also with the changing series field flux. So the compound motor torque curve falls somewhere in between the two. So again, they both have their applications. The cumulative or the compounded motors definitely have the combination of best of both worlds kind of scenario. Last thing to talk about is speed regulation. So we talked about this a bit in third year. Again, not too terrible, just making sure we have the right things in the right spots here. So motor speed regulation describes the variation of motor speed as the load on the motor changes. If the motor is able to maintain a nearly steady speed as load changes, it has a good speed regulation. So a shunt would have good speed regulation. Very little change from no load to full load. Speed regulation is a comparison of no load to full load. So we'd have the two different speeds divided by our full load. So again, if these numbers were very similar, we would have a decent percent regulation. Percent speed regulation varies depending on the type of motor. Speed regulation of a series motor is very poor because as load is added, the speed decreases substantially. So we're going to have poor speed regulation for the series. So when we do our labs, we're going to hook up a shunt, series, and compound motor, and we're going to compare all the different curves, and we're going to compare the speed regulations as well. So there's an example. Again, I usually do on the board. It's right out of your module. So we'll revisit some of this stuff again when we do lab, but that's the lab we're going to do is we're going to hook up these motors and see what they do in regards to speed as we load them up and check out their curves.